Analyses.
Hello and welcome to a Gilli Pong analysis. Okay, so I want to continue our journey into analyzing the things that we have seen in the past videos. We have been analyzing different things, for sure. And I have found that there is a certain lack of foundation of knowledge in the fields of science. And I hope you understand what I'm talking about when I am going there. For instance, interferometry and an algorithm to create a picture of a black hole 27,000 light years away. That is, without a doubt, complete bullshit. But to the average normal person out there, we have gotten a photograph of a black hole. Okay. So now, in this video, I want to go into gravity. Shh! Yoshi! So gravity is what keeps this scientific solar system theory together. Yes, theory. Because most of what they're talking about are theories. And there was one comment on one of my videos that there's a difference between a regular theory and scientific theory. But the root word is theory, concept, an idea. So what I found out just by researching a little bit about it, that the gravity, where two masses are attracted to each other, creating gravity, and that holds the oceans on a globe, according to the official scientific research, is all holding together. The Big Bang, everything, all the ideas about this are on the Cavendish, Henry Cavendish, who in 1797 and 98 created an experiment, creating an experiment where he could see this theory of gravity and the constant of gravity. So Newton got the apple on his head, and he made a measurement of how fast things fall to Earth, while Cavendish got some information about it. Let's just go into this video from a very nice individual, Physics Almanac, on YouTube. I thought this was a nice one because he's just going through the whole thing. Henry Cavendish was a very peculiar guy. He only talked to men. And he had women servants whom he only talked to using notes. It was kind of like this guy from Christmas Carol, Scrooge, so really rich guy in the 1700s, 1800s, early 1800s. It's a very interesting fellow to check out. But yeah, let's just go through this And I'll stop and try to give you a little information from what I have researched.
In this video, we're going to go over the first ever experiment to determine the Earth's mass. I've rated the physics level in this video as intermediate. This is a very famous experiment called the Cavendish experiment, named after Henry Cavendish, although it was
Yeah. Like I talked earlier about, this is about weighing the Earth. Figuring out the mass of the Earth. And that is where we get all the equations about gravity.
It was actually designed and built by another man named John Michell. Unfortunately for Mr. Michell, he designed the whole thing and he built the apparatus, but then he died before he could carry out the experiment, and his apparatus eventually made its way into the hands of Henry Cavendish. Cavendish carried out this experiment in the late 1700s. He was a British aristocrat and a bit of an odd character. He was extremely antisocial and refused to interact with anyone except for a handful of friends. This resulted in him making numerous discoveries in private, but no one ever knew about him because he never published them.
He never published anything. If you're a scientist, usually you publish something and then it's refuted and then it's peer reviewed and stuff like that, right? But not in Henry Cavendish's case. John Michell died. John Michell was also a kind of a funny dude. And he, like, they met in the Royal Society. And Henry Cavendish was also the discoverer of hydrogen, which is also very, very interesting. Fascinating. We could go into that later, but it's a whole other realm. But in this case, Mitchell, and here is this mechanism where this was all figured out. And he's going to go into this. This is the mechanism Henry Cavendish got after the death of John Michell.
And so most of his discoveries ended up being credited to later scientists who made them independently. It wasn't until many years after his death that people read his notes and realized he had made all these discoveries first. Today's experiment, however, because it had been designed and set up by John Michell, was publicly known before Cavendish ever got his hands on it, and so it's one of the few that he actually got credit for. So let's take a look at what he did. At the time, Newton's universal law of gravitation had already been discovered, and it states that the attractive gravitational force between two objects, with masses big M and little m, is equal to some constant capital G, which is now known as Newton's constant, times the product of the two masses, divided by the distance between the two squared. And so, for an object sitting on the surface of the Earth, the gravitational force it will feel is capital G times the mass of the Earth times the mass of the object, divided by the distance to the center of the Earth, which is just the radius of the Earth. This can be rewritten as the mass of the object times little g, where little g is just the acceleration due to gravity at the surface of the Earth, and it's equal to capital G times the mass of the Earth divided by the radius of the Earth squared. And this value is easily measured and is equal to 9.8 meters per second squared. Now notice that both sides of the equation have the mass of the object, so they can divide out. And if we now multiply by the radius of the Earth squared, we get that the product, capital G times the mass of the Earth, equals the radius of the Earth squared times little g. Now the radius of the Earth was already known at this time, and if you want to know how that was measured, I have two videos explaining two separate methods, one by Eratosthenes and one by Al-Biruni. And so it was already known that the radius of the Earth was about 6.4 million meters.
6.4 million meters. This experiment that was done in 1798 has never been done again. No one has done this experiment. And the equations, the findings from this notebook from Henry Cavendish is what everybody just believes in. Belief system.
This meant that the product of Newton's constant and the mass of the Earth was known. The problem was...
And Aristophanes, and whatever his name is, this guy here, who figured this out, that's like 2,000 years ago. 3,000 years ago. These guys figured that out. The radius of the Earth.
The individual terms were not known, only their products. And so in order to separate them, you either have to somehow find the value of Newton's constant or the mass of the Earth. So this brings us to the Cavendish experiment, which is going to end up measuring Newton's constant. But Cavendish called his experiment Weighing the Earth, in part because it's a much more impressive title, but also because if you measure Newton's constant, you can figure out the mass of the Earth. So you get two birds with one stone. So here's what Cavendish did. He took a rod with two masses on each end, each with mass little m, and the rod had a length, which I'm going to call 2L. He then attached what's called a torsion wire to the center of the rod. I'll get into what a torsion wire is in a second. And then he hung the rod from that wire. In this diagram, this is a top view, and you're looking down on the wire. Then he put two large masses next to each of the little masses on the rod. And these large masses are fixed to the ground. They can't move. The rod can swivel, but the large masses can't move. And we're going to say that the green mass and the blue mass are separated by a distance d. Now, according to Newton, the blue mass is going to feel a gravitational attraction to the green mass. And same thing on the other side. If you're finding this video interesting so far, please consider liking and subscribing.
Yeah.
And please share it with a few friends.
Check this guy
I'm
out.
going to draw a side view of this just to make sure it's clear what's going on.
So side view.
Here we have our torsion wire, and hanging from it is the rod with the blue masses on each end. And then we place the larger green masses.
You can also help us out here. This is like the side view of it. Get it?
Is next to the blue masses. And so the blue mass feels a gravitational attraction to the green mass. We can now write down what the gravitational force is, and notice that in this case, unlike in the case with the Earth, we know both masses, which means the only thing we don't know here is Newton's constant. And so if we can measure this force, we can figure out what Newton's constant is. And the way we're going to do this is we're going to use torque. Now torque is just the force multiplied by the lever arm, which is the distance from the center to where the force is applied. So in this case, that's going to be the force of gravity times half the length of the rod, which is just L, and then the whole thing's multiplied by 2 because you got one on each side. This is going to cause the rod to rotate in a counterclockwise direction as viewed from the top. So now let's explain what a torsion wire is. Well, it's basically just a wire, but it's got some stiffness to it, so it resists being twisted. And specifically, it resists in the following way. If you twist the wire by some angle, which I'm going to call theta, then the torque in the wire trying to undo the twisting is equal to some constant, which I'm going to call K, times the angle theta. And it's got a negative in front to indicate that it's trying to twist back. This constant K is determined by properties of the wire, and it can easily be figured out by running some experiments with known torques on the wire. So going back to Cavendish's experiment, what's going to happen? The force of gravity is causing a torque that's trying to rotate this bar, but the wire doesn't want to rotate, so it's resisting it. So what's going to happen is the force of gravity is going to try to rotate this bar, And the resistance in the wire is going to try to undo that rotation, and at some point the torque due to the gravitational force is going to equal the torque in the wire, and the whole thing's going to stop. And so at this point, the net torque, which is just the torque from gravity plus the torque in the wire, is equal to 0. So we can plug in our expressions for the two torques, and now all we have to do is measure how much it rotated, meaning we got to measure this angle theta. I say all we have to do, but this is actually more difficult than you might think. Because the force of gravity is very weak. I know it doesn't seem like that, but that's just because the Earth is so enormous.
It's so big.
But in this case, these masses we're using are much smaller than the mass of the Earth.
Yeah.
So these forces are very tiny, and so this whole apparatus is very sensitive to anything else that might cause it to rotate.
Yeah.
In fact, it's so sensitive that Cavendish couldn't get anywhere near this experiment because his own gravity will mess it up.
His own gravity would mess it up. That's how delicate this experiment was. Henry Cavendish's own gravity. I don't know if it was gravity towards him because he was very big, or if it was gravity on Earth while the experiment was being taken place. Let's see.
Not only that, he had to make sure there was nothing else, even air currents, that could possibly affect the rotation of this bar. I found this blurry picture depicting how he dealt with this problem. What he ended up having to do was enclose his entire experiment inside an airtight room. Now, in this picture, they put a big hole in the wall so you can see that the experiment's inside, but in reality, this hole wasn't there.
Oh, the big hole here wasn't here. And it was an airtight room.
Then he poked a hole in the wall and measured the angle of rotation by looking at it through a telescope. Now, since he had to know the gravitation...
But this is just like a drawing of it. Because he didn't publish anything, or maybe he drew this of himself in the notebook. We're not very sure of that.
Force, he also needed to know the distance between the two balls. But he was clever, and he realized that if he set his experiment up properly, he could use the measurement of the angle to infer the distance. And so he only had to measure the angle. Going back to the torque equation we derived, we have 2 times F sub g times L equals K times theta. And now we've measured theta. We can now plug in Newton's law of gravitation into the force of gravity, and then solve for Newton's constant. Now recall, in the case of the Earth's gravitational force, we only knew the product of Newton's constant and the mass of the Earth. But now we have Newton's constant, and so we can solve for the mass of the Earth. But actually, I'm not going to do that just yet, because Cavendish, in his experiment, didn't report the mass of the Earth. Instead, he reported the density of the Earth, or I should say the average density of the Earth.
So he didn't weigh the Earth. Just saw how dense it was.
I'm going to call rho. And if you know the average density of the Earth, you can figure out its mass just by multiplying by the volume of the Earth, which is just the volume of a sphere with the radius of the Earth. You'll see in a minute why he chose to report the Earth's density instead of its mass. So now let's substitute the Earth's mass with its volume times its density, and we can cancel out an r squared from both sides to find that the density of the Earth equals 3 little g divided by 4 pi times the radius of the Earth times Newton's constant. And so Cavendish conducted his experiment, and he found that the average density of the Earth was just under 5.5 grams per cubic centimeter, which implies that he found the mass of the Earth to be 5.9 times 10 to the 24 kilograms, and Newton's constant to be 6.74 times 10 to the minus 11 meters cubed per kilogram per second squared. Comparing his results to the modern values, we can see that he was very accurate. So now, why did he report the Earth's density in...
So modern values, comparing his stuff to modern values, where we haven't weighed the Earth. It's like very close. It's kind of almost the same, but they added like a 972. 5.97, not 5.90, 5.7, and it's also like 5.514 grams per cubic.
Instead of its mass. He did this because densities of various elements were known. And it turns out that there's not a lot of elements on Earth that are both abundant and have a density somewhere around 5.5 grams per cubic centimeter.
Cubic centimeter.
In fact, there's only one, and that's iron.
It's only iron.
So actually, he didn't get 2 birds with one stone, he got 4.
Got 4 birds with one stone.
He figured out the mass of the Earth, its average density, and he figured out that a substantial fraction of the Earth had to be iron, which it turns out, today we think it's about 35%. If you enjoyed this video, stay tuned and subscribe for the next video in this series.
Thank you so much, Physics Almanac. This is brilliant. So, this is something that CERN, CERN, are using. Everybody is using these equations as describing the Earth's gravitation pull towards the sun, the moon, all the other wandering stars, which are called planets today. And they've never like redone this experiment for some reason. They just use this experiment as a reference. Like all these scientists, all this money, all these studies does not kind of go into figuring this stuff out. And Cavendish, he died at Clapham. It was near Clapham Common. I actually went to Clapham Common in London last summer. It's very interesting. My son met one of NBA stars while playing basketball in Clapham Common Garden. Steve Adams. He met him. Interesting synchronicity here. But he died in 1820, 24th of February, as one of the wealthiest men in Britain, and was buried along with many of his ancestors in the church that is now known as Derby Cathedral. So this is one of the richest guys in England in 1810. Not 1820, if I said that earlier. University of Cambridge. Yeah. My question would be, why hasn't this experiment been redone using modern technology and understanding? And gravity is just gravity, according to everyone. But I don't feel this holds any real water. It's like a belief. Because it's an observation of something. And then there's a very weak experiment made like 300 years ago. Or 200 years ago. And it was all from notebooks. Makes you wonder, doesn't it? This is a belief system. But anyway, it's time to shine. So let's glow. And thank you so much for watching. Like, comment, and subscribe if you like videos like this. And I will try to continue my journey into analyzing this particular weird belief system. Until next time. Ha det bra!
Gilli Pong!
Analyses.